Module 2, Lecture A, Cleaning Engineering Data. By the end of this lecture, you will be able to detect missing, duplicated, inconsistent, and physically unrealistic values in engineering datasets, clean tabular and time series data using transparent Pandas and NumPy operations, and document data cleaning decisions so model results remain traceable and defensible. Data quality checks. Missing value detection. Missing values in engineering datasets must be detected because they can distort analysis and lead to poor decisions. They may appear as blanks, placeholders, or error codes, so identifying them depends on understanding how the data was collected and which fields are critical. For example, a missing vibration sensor reading may matter far more than a missing comment because it could affect machine fault detection. When checking missing values, look at both how many are missing and where they occur. A few scattered gaps may be normal, but gaps that cluster around certain times or conditions can signal data collection problems. For example, missing wind turbine power data during high winds may point to shutdowns or sensor failures, so engineers should consider whether the gaps match known events and how they affect interpretation. Detecting missing values means separating truly absent data from values that are wrongly encoded. Engineering systems may use placeholders for sensor faults or communication errors, such as negative readings or zeros, which can be mistaken for valid measurements. Context is essential because the same value may be valid in one operating state but invalid in another. The goal is to make missing data clear and interpretable so analysis and models are reliable. Python code, missing value detection. Detect missing values in engineering data by using Pandas masks to make the checks clear and transparent. Before deciding how to clean the data, summarize where the gaps are and how extensive they appear. The script begins by importing NumPy and Pandas, two core libraries for data work in Python. NumPy supports efficient array operations and mathematical processing, while Pandas provides data frames for working with structured data. Together, they prepare the script for later data manipulation and analysis. We create a small pump sensor dataset to mimic real-world data quality issues. It includes time, pressure, flow rate, and operator notes, with examples of missing values, fault codes, empty notes, and unavailable entries. This gives us a simple test case for cleaning and handling imperfect sensor data later in the script. The data dictionary is converted into a Pandas data frame, turning the raw data into a structured table. Its keys become columns, and the stored values form the rows. This format makes the data easier to analyze, manipulate, filter, aggregate, and check for missing values in later steps. To handle missing data, first identify text entries that represent missing values, such as blank fields or not available. Then use the data frame replace method to convert those placeholders into NumPy missing value markers. This makes the dataset's missing data consistent and easier to clean and analyze. Fault values are defined for each sensor column, such as -999 for pressure and -1.0 for flow. These values are then replaced with missing values using the data frame replace method. This marks faulty sensor readings as missing, making the data cleaner for later analysis. To assess missing data in a data frame, first count the missing entries in each column using the isMissing check and a sum. Then, calculate the percentage missing by averaging those missing value indicators and multiplying by 100. Round the results to one decimal place to make them easier to read. To find rows with missing data, check each row of the data frame for missing values and keep only the rows where at least one value is absent. Then take the time column from those rows and turn it into a list of time points. This identifies when incomplete data occurred, making it easier to investigate the issue. A Pandas data frame can summarize missing data by showing for each column both the number and percentage of missing values. This gives a quick overview of where data is incomplete and supports decisions about cleaning or imputing the dataset. First, review a summary of missing values by column, including both counts and percentages, to see how much data is incomplete. Then, identify the rows with any missing values to locate the affected time points. Before choosing an imputation or cleaning method, investigate possible sensor faults so the decision is based on the likely cause of the missing data. This script uses Pandas to check a small pump sensor dataset for missing data. It treats empty entries and known fault codes as missing values, then reports the count and percentage of missing values in each column. It also identifies the time points where any row has gaps, helping highlight possible sensor faults that should be investigated before choosing how to fill in the data. Duplicate data. Duplicate data occurs when the same engineering record appears more than once, either exactly or with small changes. It can result from repeated sensor transmissions, manual entry mistakes, or combining data from different systems. If not handled, duplicates can distort results by overemphasizing certain observations, such as averages or failure rates. Detecting and managing them is essential for reliable analysis and data-driven decisions. To find duplicates in engineering data, first define what makes each record unique, such as a serial number or a combination of equipment ID, timestamp, and sensor channel. The same values may signal a duplicate, but some matching fields can still be valid depending on how the data was collected. Also check for near duplicates caused by differences in formatting or capitalization. Good duplicate detection combines data analysis with engineering knowledge of the system. Duplicate data should be interpreted, not removed automatically, because its meaning depends on the analysis. Some duplicates are errors, while others may represent valid repeated trials, inspections, or stable measurements. Engineers should look for patterns across time, equipment, and production areas to decide whether duplicates are isolated or systematic. The goal is to keep records that reflect real observations while reducing bias and improving model reliability. Python code duplicate data. Duplicate rows can distort engineering summaries, so they should be identified and handled carefully. Pandas can help detect both exact duplicates and duplicates based on selected context, while keeping cleaning choices traceable. The script starts by importing Pandas and NumPy, two core libraries for data work in Python. Pandas helps manage and analyze tabular data, while NumPy supports efficient array operations and mathematical processing. Together, they prepare the code to handle data effectively in later steps. We begin by creating a small sample dataset that simulates vibration records. It includes asset names with slight naming variations, timestamps, and sensor types such as vibration and temperature. This gives us a simple foundation for examining how duplicate entries can be identified and handled. The code organizes sensor readings into a dictionary for creating a data frame. It stores 6 values, 3 readings of 0.42, and 3 temperature readings of 185, 185, and 188. A matching units list labels the first 3 values as inches per second and the last 3 as degrees Fahrenheit, making the data ready for structured analysis. We create a Pandas data frame from the data dictionary to organize the data into rows and columns for easier analysis. Then, an assertion checks that the data frame has 6 rows and 5 columns, confirming the data loaded as expected and helping catch errors early. The code uses the Pandas duplicated method to find rows that match exactly across all columns. by marking every occurrence of each duplicate. It can count the total number of repeated rows. This count helps assess data quality and supports cleaning the dataset. The code normalizes asset labels so duplicates are easier to detect. It makes labels uppercase, replaces spaces with dashes, and standardizes the pump label pump-07 as pump-7. These changes reduce naming differences that could otherwise hide duplicate assets. Create a checked copy of the original data and add a column with standardized asset labels, so the source data remains unchanged for traceability. Then define the key fields used to detect contextual duplicates, including the cleaned asset label, time, sensor type, value, and unit. These fields set the criteria for identifying duplicate records during cleaning. To find duplicates using engineering rules, we check the data frame for repeated records across key fields such as the cleaned asset label, timestamp, sensor type, value, and unit. By marking every matching record as a duplicate, we can count the full set of contextual duplicates. This gives a clear total of records that meet the defined duplicate criteria. We remove duplicate records by using the data frame drop duplicates method with the columns that define uniqueness for our rules. Only the first record in each duplicate group is kept. Then we compare the original row count with the cleaned row count to see how many duplicates were removed and measure the effect of the cleaning step. The code records a clear decision about data cleaning. After asset labels were normalized, duplicate records with the same asset, time, sensor, and value were removed. This documentation makes the cleaning process easier to trace and understand. The cleaning summary reports the row count before processing, then shows how many exact and contextual duplicates were found. Contextual duplicates are identified using key engineering fields such as asset, timestamp, and sensor. It then reports how many rows were removed and how many remain, ending with a brief decision statement that documents the cleaning action for traceability. This script cleans a small set of vibration and temperature readings by finding duplicate records and standardizing asset names. It checks for exact duplicates across all columns, then identifies contextual duplicates after making labels consistent. Redundant rows are removed while keeping the first record in each group. The output reports the row counts before and after cleaning, the duplicate counts, and the number of removed rows, with the removal decision documented for traceability. Inconsistent values. Inconsistent values in engineering datasets are hard to notice because they may look valid while using different units or naming formats. For example, measurements or material grades can appear in multiple forms that mean the same thing. These inconsistencies can distort summaries and cause models to learn data entry patterns instead of real behavior. So values should be checked for consistent, comparable representation across the dataset. To find inconsistent values, compare each data field against the engineering rules it should follow. Check categorical data for spelling, capitalization, abbreviations, and valid categories, and check numerical data for consistent units, decimal placement, and sign conventions. These checks help protect the technical accuracy of the data before analysis or modeling. Data quality checks should look for inconsistencies across related fields and over time, not just unusual individual values. Examples include a closed valve with high flow, a battery state of charge above 100%, charging shown during discharge, or manufacturing records with impossible machine or timing relationships. These issues should be flagged for investigation because resolving them often requires engineering judgment, additional records, or system knowledge. Python code. Inconsistent values. Use Pandas to detect inconsistent engineering values by checking categories, units, and expected relationships. Flag potential issues first, so the raw data is not changed before problems are reviewed. The script begins by importing Pandas and NumPy, two common tools for data processing. Pandas is used to organize and work with structured data through data frames, supporting tasks like filtering, mapping, and summarizing. NumPy provides numerical computing support, though its role here is limited. We create a small pump test dataset to support later checks for data inconsistencies. It includes pump identifiers, operating status, pressure readings in kilopascals, and flow rates in liters per minute. The entries intentionally use varied labels and status terms, and some pressure values may suggest mixed units, making the dataset useful for detecting irregularities. First, we load the dataset into a Pandas data frame, so the raw data is organized in a structured form. This makes it easier to access, transform, standardize, and check the data for inconsistencies in later steps. Pump identifiers are standardized, so they can be compared consistently. Each ID is converted to uppercase, and underscores are replaced with hyphens. This creates one consistent format for easier analysis later. A status mapping dictionary standardizes different status descriptions into common labels. For example, variations like run and on are grouped as running, while closed is grouped as closed. This keeps status values consistent across the dataset, making analysis and comparison easier. The code standardizes the status column by converting its text to uppercase, so comparisons are not affected by letter case. It then maps those values to common status labels using a predefined status map. This normalizes different status descriptions into a consistent format for easier analysis and comparison. We check the pressure data for possible unit mix-ups by looking for values that are unusually low for kilopascals. Because 1 bar is about 100 kilopascals, pressures between 1 and 5 kilopascals may actually have been recorded in bars. A between check flags these suspicious values in a new column, making them easier to review and correct. A new data frame column flags possible data errors where a pump is marked closed but still shows a flow rate above 5 liters per minute. Rows meeting both conditions are labeled as closed with high flow, highlighting a likely logical inconsistency. A summary dictionary is used to count key data inconsistencies. It tracks pump naming variants by comparing standardized and original identifiers, counts statuses that could not be cleaned, flags pressure values that may use the wrong unit, and identifies cases where a closed pump still shows notable flow. These counts provide a quick overview of possible data quality issues. The script prints a short message to introduce the inconsistency check results, then displays a summary of the issues found in the dataset. This summary gives counts for key data quality problems such as inconsistent pump names, unmapped status values, possible unit mix-ups, and conflicts between status and flow data. Together, these outputs provide a concise report of the checks performed earlier. The data frame is filtered to flag possible data issues, such as pressure values that may be recorded in bars instead of kilopascals, or closed valves that still show notable flow. Only the key fields, including pump ID, status, pressure, and flow rate, are selected for review. The filtered results are then printed without row indices, so the potential inconsistencies are easy to inspect. This script checks pump test records for likely data inconsistencies. It standardizes pump names, groups status descriptions into common labels, and flags suspicious cases such as pressure values that may use the wrong units, or closed valves that still show flow. The output summarizes naming variants, unmapped statuses, possible unit problems, and status flow conflicts, then prints the key rows that need review. Core cleaning operations. Unit standardization. Unit standardization makes engineering data consistent and reliable when measurements come from different sources. Values such as pressure or temperature must be converted to chosen target units, so calculations and models are not distorted. These conversions should be clearly documented and transparent in Pandas and NumPy workflows, so others can understand the data preparation and apply models correctly to new data. First, find where units vary and separate measurement values from their units, whether the units appear in headers or inside cells. Clean mixed columns so numbers are distinct from text and symbols, especially when combining data from different sources. Then use Pandas for consistent column conversions and NumPy for efficient large-scale transformations, keeping the process systematic and reproducible. Unit standardization requires context, not just mechanical conversion. Temperature conversions may involve both scaling and offsets, and pressure values can differ in meaning depending on whether they are gauge or absolute. Use engineering judgment when data affects important decisions or models. Then check converted values against expected ranges. Keep the original data and document assumptions so the process remains traceable. Python code. Unit standardization. Standardizing units helps prevent hidden errors in engineering calculations. In this example, raw values are kept for traceability, while Pandas applies explicit rules to convert mixed units consistently. We begin by importing NumPy and Pandas, two core libraries for working with data. NumPy supports numerical operations, while Pandas helps with data manipulation and analysis. We begin by creating a small pump test dataset with mixed units. It includes test identifiers from A to E and flow rate measurements for each test. The flow values use different units, which will be standardized later. The script sets up test data with mixed flow and pressure units. Flow rates use units such as liters per minute, cubic meters per hour, gallons per minute, and cubic meters per second, while pressures are given in kilopascals, bars, pounds per square inch, and pascals. This prepares the data for later conversion into standard units. We first use Pandas to turn the raw data dictionary into a data frame containing the initial measurements, including mixed units. Then we make a deep copy to preserve the original data before any cleaning or transformations, so it can be referenced later if needed. This defines conversion factors that standardize flow rates into cubic meters per second. Liters per minute, cubic meters per hour, and gallons per minute are each scaled by the appropriate factor, while cubic meters per second use a factor of 1. This makes flow measurements consistent across different units. A pressure conversion dictionary maps common pressure units to their values in pascals, such as pascals, kilopascals, bar, and psi. This makes it easy to convert different pressure measurements into pascals, giving calculations a consistent standard unit. The code standardizes measurements by converting flow values to cubic meters per second and pressure values to pascals. It does this by multiplying each value by the appropriate conversion factor for its original unit. Using consistent units makes comparisons and calculations more accurate. The code checks for unsupported flow and pressure units by looking for missing values after unit conversion. It uses the Pandas missing value check to count these cases in each column. Any missing converted values indicate units that were not included in the conversion mappings and may need review or correction. After converting units, the data is checked for unusually high values. Flow rates above 0.01 cubic meters per second and pressures above 500,000 pascals are marked for review, while values within those limits are marked as acceptable. This helps identify measurements that may be physically unrealistic or unexpected. A compact, clean view data frame is created by keeping only the key review fields: the test identifier, standardized flow and pressure values, and flags showing whether either value needs checking. This gives a concise summary of the essential data for review. The output first states the standardized target units, cubic meters per second for flow, and pascals for pressure. It then reports how many flow and pressure units could not be converted, shows a cleaned and rounded version of the standardized data without the index, and lists the original raw column names to confirm they are preserved for traceability. This script standardizes pump measurement data by converting flow rates to cubic meters per second and pressures to pascals. It applies unit conversion factors, identifies unsupported units, and flags unusually high flow or pressure values for review. The output shows the clean, standardized data while preserving the original raw columns for traceability. Outlier handling. Outlier handling means identifying unusual data values and deciding how to treat them before analysis. In engineering data, these values may come from errors like sensor noise or calibration problems, but they can also reveal real equipment issues. Tools such as Pandas and NumPy can help filter, flag, or adjust outliers transparently, which matters because extreme values can strongly affect averages and models. Handle outliers first, with engineering judgment and known physical limits. Then use statistics to find subtle problems. Impossible values, such as temperatures below absolute zero or efficiencies above 100%, should be rejected immediately. For the remaining data, use percentiles and medians in tables, and compare each time series point with nearby values. Always interpret statistical flags in context, since a value that is normal during startup may indicate a fault during steady operation. Handle outliers based on why they occurred and how the data will be used. Clear errors, such as sensor glitches or entry mistakes, should usually be marked as missing, while extreme but plausible values may be capped to reduce their influence. If an outlier represents a real event, keep it and consider flagging it, because removing it could hide important information. For time series, preserve the order and distinguish brief spikes from longer shifts that may signal real change. Tools like Pandas and NumPy can help apply these decisions consistently and track what was changed. Python code, outlier handling. This section demonstrates a transparent approach to handling outliers in small engineering sensor data. The goal is to identify and manage unusual readings while preserving the original values so the data remains traceable and auditable. We import 3 core libraries for data analysis: NumPy for efficient numerical and array operations, Pandas for working with structured tabular data, and matplotlib/pyplot for creating visualizations. Together, they provide the basic tools needed to analyze data and inspect patterns or trends visually. The dataset begins with time points from 0 to 11, created using NumPy's range-style function. It includes pressure readings in kilopascals and flow rates in liters per minute over the same period. Both measurements contain unrealistic outliers, such as an extremely high pressure value, a negative pressure value, and an unusually high flow rate, which will be used to study outlier handling. We use Pandas to create a data frame that organizes the sensor data into columns for time, pressure, and flow. Each column comes from the corresponding NumPy array, making the data easier to manage and analyze. Before cleaning the sensor data, we save the original pressure and flow readings in separate columns. This keeps a traceable record of the raw values so they can be compared with the clean data later. Preserving these originals helps show what changed during the cleaning process. Pressure readings below zero are treated as physically impossible and marked as invalid. Those invalid values are then replaced with not a number, so they are clearly flagged and excluded from later analysis. This helps protect the integrity of the dataset. To assess the spread of the flow rate data, we find the first and third quartiles, which mark the points below which 25% and 75% of the values fall. The interquartile range is the difference between these two quartiles, showing the spread of the middle half of the data. This measure is useful for detecting possible outliers. To handle outliers in the flow data, we first set lower and upper limits using the interquartile range around the first and third quartiles. Then we apply the clip method to cap any values outside those limits. Values below the lower limit are raised to it, and values above the upper limit are reduced to it, making the data more robust while keeping its overall structure. We compare the original flow readings with the capped values to identify which data points were changed. A new Boolean column marks whether each flow value was capped, making it easy to track adjustments made during outlier handling and keep the data cleaning process transparent. The summary reports the dataset size, then counts how many invalid pressure values were replaced and how many flow values were capped. It also shows the lower and upper flow capping limits, rounded to 2 decimal places. Together, these outputs give a quick overview of the data cleaning results. We filter the data to show only rows where cleaning changed something, such as invalid pressure readings or capped flow values. Then we review key columns, including time and the original and cleaned measurements. This makes it easier to verify the cleaning steps and keep the data changes transparent and traceable. This plot compares original flow readings with capped cleaned readings over time. The original data is shown with dashed lines and circles, while the capped data uses solid lines and squares. Axis labels, a title, a legend, and a grid make the chart easier to interpret and help highlight how outlier handling changes the flow measurements. This script shows how to clean engineering sensor data while keeping the process traceable. It stores pressure and flow readings, marks impossible pressure values as missing, and caps extreme flow values using robust quartile-based limits. It then reports how many values were changed, shows the affected rows, and compares original and cleaned flow data in a plot. The goal is transparent outlier handling that supports reliable engineering analysis. Time series cleaning. Time series cleaning prepares data recorded over time by checking both the values and their timing. A reading can be wrong if it is out of order, duplicated, recorded at the wrong time, or changes in an impossible way. The key first step is to create a reliable time index by parsing timestamps consistently, sorting them, and aligning them to the expected frequency. This makes later analysis, such as interpolation and event detection, more trustworthy. Cleaning time series data requires handling missing values, irregular sampling, and duplicate timestamps in a way that fits the engineering context. Short gaps may be interpolated when safe, but gaps that could hide critical events should not be filled blindly. Duplicate timestamps may need removal, aggregation, or separation depending on their source. When combining data sampled at different rates, resampling with tools like Pandas and NumPy helps make averaging, summing, and interpolation explicit and reproducible. When cleaning time series data, the aim is to reduce noise and fix artifacts while preserving meaningful signals. Sensor spikes and random fluctuations can mislead models, so smoothing methods such as rolling statistics or window-based filters should be used carefully. Time alignment is also important for comparing related events, such as commands and system responses. Overall, clean data should remain accurate, transparent, and reliable for analysis. Python code, time series cleaning. Time series cleaning helps protect the quality of engineering signals. Before changing measured values, first check the timestamps and make sure every cleaning decision can be traced later. We begin by importing NumPy, Pandas, and Matplotlib, the core Python libraries for data analysis. NumPy supports efficient numerical operations. Pandas helps manage and manipulate data, and Matplotlib creates visualizations. We create a small pump flow dataset by converting a few timestamps into date-time values. One timestamp is repeated to represent a duplicate entry. These timestamps become the dataset index, making it possible to track flow rate changes over time. A set of flow rates is created, including typical values and one unrealistic spike of 999 gallons per minute. These readings are combined with their timestamps to form a Pandas data frame, giving the raw data a structured format for later analysis. The data is first sorted by time, so the records are in chronological order, which is essential for time series analysis. The index is then reset to create a clean sequence, and the time column is set as the new index to support time-based operations. The data is first grouped by timestamp, so any duplicate times can be combined by averaging their flow values. This creates a cleaned dataset with one entry per timestamp. Then, a complete 1-second timestamp sequence is generated from the earliest to the latest time, making it possible to detect any missing timestamps. The data is aligned to a consistent time index by matching it to the full expected range of timestamps, covering every second from the earliest to the latest time. This makes any missing seconds visible in the dataset. The index is then named time, so it is clear that it represents timestamps for later analysis. Pump flow readings are checked to see whether they fall within the realistic range of 0 to 200. A copy of the aligned data is then cleaned by marking any values outside that range as missing. This flags physically impossible readings so they can be handled properly in later analysis. Short gaps in the flow data are filled by interpolation, but only when a single value is missing between known values. Then a 2-point rolling mean is applied, averaging each value with the previous one to smooth the data and make trends easier to see. A decisions list is used to record the main data cleaning actions, such as sorting timestamps, handling duplicates, filling missing 1-second intervals, removing impossible spikes, interpolating short gaps, and applying a small rolling mean. This creates a clear audit trail, so each cleaning choice is transparent and easy to review later. The cleaning summary compares the raw and clean data sizes, then reports missing flow values found after timestamp alignment. It also shows how many unrealistic values were removed as outliers. Finally, it records the cleaning decisions to provide a clear audit trail of the process. This plot compares raw and cleaned pump flow readings over time. A new figure is created, then the raw data is shown with dashed lines and circle markers, while the clean data is shown with solid lines and square markers. The axes label time and pump flow rate in gallons per minute, and a title and legend make the comparison clear before the plot is displayed. This script shows how to clean pump flow time series data by sorting timestamps, averaging duplicates, and making missing time points explicit. It removes unrealistic flow spikes by marking them as missing, then fills short gaps with interpolation, and smooths the result with a rolling average. It also reports key cleaning statistics and compares the raw and cleaned signals, supporting transparent data preparation for engineering applications where signal quality matters. Traceable cleaning decisions. Cleaning decision logs. A cleaning decision log records what changes were made to a dataset, why they were made, and how they may affect later analysis. It connects raw data to final conclusions and helps future engineers understand the path from original values to cleaned results. For example, if impossible sensor readings are marked invalid, the log should note the issue, the decision, and who made the change. Cleaning decision logs help preserve transparency in engineering datasets, where data may come from different sources and carry different uncertainties. They should record key choices, such as unit conversions, gap handling, and the reasons behind those edits. By documenting these decisions clearly, engineers make their judgment traceable and protect the integrity of the dataset. A cleaning decision log should record the key choices that affect results, such as how outliers or timestamp changes were handled, without documenting every minor action. It should make the reasons for important changes clear, especially when data is altered because of equipment limits rather than real process behavior. This creates traceability from cleaned data back to the original data, and shows that decisions were transparent, defensible, and open to review by teammates or auditors. Python code. Cleaning decision logs. Cleaning logs make data engineering edits traceable and easier to defend. Even small examples can show why changes were made, and Pandas can record those changes alongside the clean data. The script starts by importing Pandas and NumPy, two core libraries for data work. Pandas helps manage and analyze tabular data, while NumPy supports numerical operations. Together, they provide the foundation for the data cleaning and manipulation steps that follow. We create a small sample dataset to mimic raw sensor readings for time, engine speed, and temperature. It includes common data quality problems, such as a duplicate timestamp, a negative speed value, a missing speed value, and an unrealistically high temperature. These intentional issues make the dataset useful for practicing basic data cleaning. The raw sensor data is first loaded into a Pandas data frame to preserve the original records. A separate copy is then used for cleaning, so the source data remains unchanged. An empty decision log is also created to record each cleaning choice and its reason. We remove repeated timestamps from the clean data frame by marking duplicate values in the time column while keeping the first occurrence. The duplicate mask is summed to count how many repeats were found. The data frame is then filtered to keep only unique timestamps, and a copy is made to preserve the cleaned result. A new entry is added to the decision log to document how duplicate timestamps were handled. It records the issue, the rule of keeping the first duplicate record, and the number of affected rows based on the duplicate count. Negative values in the RPM column are identified because they are not physically valid in this context. The affected entries are counted. Then those invalid readings are replaced with missing values. This marks the data properly for later analysis or correction. The code adds a new record to the decision log to document a data cleaning step. It notes that negative RPM values were found, records the rule of marking those invalid values as missing, and stores how many rows were affected. This makes the cleaning process easier to trace and justify. To clean the temperature data, readings above 200 degrees Celsius are flagged as unrealistic. The flagged entries are counted to measure how many values exceed the limit. Then those values are replaced with not a number to mark them as invalid and keep the data within a realistic range. The code adds a new item to the decision log to record a data cleaning choice. It notes that some temperature readings are above the sensor's calibrated range, so those invalid values are marked as missing. The log also stores how many rows were affected based on the previously identified high temperature readings. We first count the missing values in the RPM column to establish a baseline. Then we use linear interpolation to fill only short gaps, allowing at most one missing value in a row to be estimated from nearby data. Afterward, we count the missing RPM values again to see how much the interpolation reduced them. The code adds an entry to the decision log to record how short gaps in the RPM data were handled. It notes that one value missing gaps were filled using linear interpolation. The entry also records how many rows were fixed by comparing the missing value count before and after interpolation. The code turns the decision log into a structured table for easier review, then compares the row counts before and after cleaning to show how much data was affected. It also reports the total missing values left in the cleaned data, giving a quick check for any remaining data quality issues. The code prints a concise decision log by converting the data frame to a readable string without showing the index. This gives a clear summary of the data cleaning decisions made during processing. This script cleans a small sensor dataset while recording each decision. It removes duplicate timestamps, marks impossible negative RPM values and temperatures above 200 degrees as missing, and fills only short one-value gaps in RPM using linear interpolation. It then reports the raw and cleaned row counts, remaining missing values, and a decision log that explains what was changed and why. Cleaning decision logs. A cleaning decision log records what changes were made to a dataset, why they were made, and how they may affect later analysis. In engineering, this connects raw data to results such as safety assessments or model predictions. By documenting issues, decisions, and who made them, the log makes data cleaning traceable and helps future reviewers understand how the dataset was transformed. Cleaning decision logs are important in engineering because datasets often combine automated readings, manual entries, and lab results with different uncertainties. When data is missing or questionable, the log should record both the cleaning action, such as leaving gaps, interpolating or excluding data, and the reason behind it. This helps preserve data integrity and lets stakeholders judge whether the cleaned data is suitable for its intended use. A clear cleaning decision log supports collaboration, replicability, and trust in an engineering project. Because data, models, and stakeholders change over time, documenting choices such as removing duplicates, standardizing units, or flagging unusual sensor values helps others recreate the cleaned dataset. It also makes it easier to tell whether changes in model performance come from real process shifts or from different cleaning methods. Python code. Cleaning decision logs. Decision logs help make data cleaning traceable by recording what was changed and why. Even small engineering tables can expose common data issues, and Pandas can keep cleaning actions documented alongside the clean data. We begin by importing Pandas, a key library for working with tabular data. It helps us clean, process, filter, transform, and summarize datasets efficiently. A small set of raw sensor records is created to demonstrate data cleaning. Each record includes a time, RPM, temperature, and gap measurement. One record contains a negative RPM value, which suggests a possible data error to identify and handle. 2 sensor records are added to the raw data to show common data quality issues. One reading has a negative RPM value, which is invalid, while the next has a missing RPM value. Both cases will need to be handled during data cleaning. This sensor record stores a time of 0803, an RPM value of 1810, a temperature of 999 degrees Celsius, and a gap of 0.020 inches. It is part of raw sensor data that will be converted into a Pandas data frame for cleaning and analysis. The temperature is clearly unrealistic, so it likely indicates a sensor error to handle during cleaning. The code converts raw sensor data into a Pandas data frame, organizing it into a clear table. This structured format makes the data easier to clean, process, and analyze in later steps. Begin by creating an empty log list to record each data cleaning decision. This makes the cleaning process transparent and traceable, so changes can be reviewed later along with the reasons behind them. Use the Pandas duplicated method to find repeated rows in the data frame. Summing the resulting true or false values gives the total number of duplicates, which can then be stored for later data cleaning logs. Duplicate rows are removed by identifying repeated entries and keeping only the rows that are not duplicates. This creates a clean data frame where each row is unique, helping maintain data integrity and improve the accuracy of later analysis. The code records a data cleaning step by logging that duplicate rows were found and removed. It also stores the number of duplicates, creating a traceable record of the action taken. We check the data for negative values in the RPM column, since negative RPM is not physically possible. Any rows with invalid RPM values are marked as missing using Pandas NA, so they can be handled properly during later cleaning or analysis. The code records how it handles negative RPM values by adding an entry to the log. The entry notes the issue, the action of marking those values as missing, and the number of affected records. This creates a clear audit trail for changes made by that rule. Temperature readings above 300 degrees Celsius are treated as unrealistic for the furnace. These values are identified and replaced with Pandas missing values, so invalid outliers are clearly marked and excluded from later analysis. The code records how it handles unrealistic temperature values. It logs that values above the chosen limit are set to missing, and it includes the number of affected entries by counting the matching true values in the mask. The code converts gap measurements from inches to millimeters by creating a new metric gap column from the existing inch values. This standardizes the data in metric units, which supports consistent engineering analysis. The code records a unit standardization step by adding a log entry. It notes that imperial gap units were converted to millimeters and records the total number of affected data frame rows, helping track consistency in the data. The code uses Pandas to turn data cleaning log entries into a structured decision log table. This makes the cleaning actions easier to review and helps trace the decisions made during data processing. After cleaning the data, we print key checks to summarize the results. This includes the number of remaining rows, the count of missing RTM values caused by invalid or negative readings, and the count of missing temperature values caused by unrealistic readings. We also print a readable decision log that summarizes each cleaning action and how many records it affected. This script cleans raw sensor data with Pandas while recording each decision. It removes duplicate rows, treats negative RPM values and temperatures above 300 degrees Celsius as missing, and converts gap measurements from inches to millimeters for consistent units. It then reports the cleaned row count, missing value totals, and a summary log, so the cleaning process is easy to trace. Defensible cleaning records. Defensible cleaning records explain why dataset changes were made and show that they support the analysis goals. In engineering, these decisions affect design, reliability, and safety, so each one should be justified with clear reasoning and sound judgment. Transparent records help future analysts, managers, or regulators understand the data and avoid misinterpreting excluded or changed values. A good cleaning record should make data decisions traceable from the raw dataset to the final model input. It should note the problem, the rule or judgment used, what data was affected, when the decision was made, and who approved it. Routine fixes need less detail, but choices that could change results, such as handling missing values near a threshold, require clear justification. In energy data, for example, keeping negative power outputs because they represent real consumption should be documented so the choice is understood later. Defensible cleaning records help show that data preparation was transparent, controlled, and aligned with engineering goals. This matters when model results are questioned or reused, especially for decisions affecting cost, operations, or safety. The records should explain key choices, such as how missing values, unusual events, or outliers were handled, without documenting every minor change. Clear records make it easier for stakeholders to trust the results and revise decisions when new information appears. Python code. Defensible cleaning records. Cleaning records help make engineering decisions defensible by documenting important changes. Even with small data, this keeps the workflow clear and transparent. We import Pandas for data manipulation and analysis, especially working with data frames. We also import NumPy for efficient numerical operations, such as handling arrays and mathematical calculations. A Pandas data frame is created to hold raw pump test readings for time, flow, and pressure. The data intentionally includes common problems, such as a duplicate time entry, a missing flow value, an unrealistic negative flow, and an unusually high pressure reading. These issues are included so the script can later demonstrate basic data cleaning techniques. The code begins by making a deep copy of the raw data, so the original remains unchanged during cleaning. It also creates an empty cleaning log to record problems found and the actions taken, giving a clear audit trail of the process. The code checks the cleaned data for repeated time values, marking duplicate timestamps after their first occurrence. It treats these repeats as likely caused by a logger reset, keeps only the first reading, and records the issue in the cleaning log with the number of affected rows, the action taken, and the reason for that choice. The code filters out rows with duplicate timestamps by using an existing duplicate mask in reverse, keeping only non-duplicate entries. It applies this filter with the data frame location method, then creates a copy so the clean data is stored separately without unintentionally changing the original dataset. We check the flow rate data for missing values, then record the issue in the cleaning log with the number of affected rows and the planned fix. Because the gaps are short and occur during a steady pump test, linear interpolation is used to estimate the missing flow values. Missing flow rate values are filled using the Pandas interpolation method, which estimates gaps from the linear trend between nearby known points. This is appropriate for a short gap during a steady pump test, where flow is expected to change smoothly. The result is a complete dataset ready for further analysis with minimal added bias. Rows with unrealistic pump data are flagged when the flow rate is negative or the pressure is above 200. These conditions identify records that violate operating limits, so the affected rows are excluded. The cleaning log records the issue, the number of rows involved, the action taken, and the reason for removal. This filtering step removes unrealistic data by excluding rows with values outside engineering limits, such as negative flow rates or excessively high pressure. By reversing the invalid condition, it keeps only rows with acceptable values. The result is a cleaned data frame that matches expected operating ranges. The code turns the cleaning log from a list of records into a Pandas table, making it easier to inspect, analyze, and export. This structured format helps keep the cleaning process clear, organized, and traceable. The code reports the row counts before and after cleaning, making it easy to see how much data remains. It then summarizes the cleaning actions in a clear table and shows a preview of the cleaned data for a quick check. Together, these outputs make the cleaning process transparent and traceable. This script cleans pump test data while recording each action so the results remain traceable and defensible. It removes duplicate timestamps, fills missing flow readings with linear interpolation, and excludes physically unrealistic values such as negative flow or excessive pressure. It then reports the cleaning summary and shows a preview of the cleaned dataset, including how many rows were removed. In this lecture, you learn to detect missing, duplicated, inconsistent, and physically unrealistic values in engineering datasets. Clean tabular and time series data using transparent Pandas and NumPy operations. And document data cleaning decisions so model results remain traceable and defensible. In the next lecture, Lecture B, we will go over features and splits.
Thank you for your attention. See you all in the next lecture.